The following is a conversation with Professor Daniel Smalley from Brigham Young University. Daniel is an extremely accomplished professor leading the lab of Smalley holography, where they try to bring the holograms that you see in movies to real life. They do this not with a headset or some pane of glass that you have to look through like most holograms that you see marketed today, but by actually grabbing particles in the air and moving them around and shining a laser on them to be able to refract light off of that particle so that you can actually see 3D models floating in the air that you could potentially someday interact with. If that sounds interesting to you, you should follow along for this week's episode and also get ready for another episode of Sci-Fi to Reality. I'm your co-host, Douglas Schonholtz, and as always, I'm joined by my other co-host, Michael Hladky. Enjoy.
Professor Daniel Smalley, welcome to Sci-Fi to Reality. Thanks for joining us.
Yeah, my pleasure.
Cool. So starting off, could you tell us a little bit about how you got into your work in the first place, working on these volumetric displays or holograms, so to speak?
So my experience with 3D displays goes way back till middle school, but our most recent work with volumetric displays is more recent. It's something that I started thinking about more carefully when I came to work as a new professor at Brigham Young University. There was a professor who still works here at the university, Justin Peatross, who had been for some years been playing with particle levitation. And for my part, I was interested in looking at scattering light off plasmas as a potential new form of 3D display. And after he heard what I was describing, he said, you really ought to take a look at some of our experiments. And once I did, I knew pretty much immediately that this was a potentially very good platform for solving a lot of the problems that we had encountered trying to create the 3D displays of science fiction.
Sure. So could we delve into those different topics then? Could you describe a little bit on what the plasma light scattering actually entails and just go from there?
Yeah, that's exactly right. So I had long believed that holography was the ultimate display technology and that it could do pretty much anything that we saw in the movies, that it could recreate almost all those displays that we associate with the future. But I went to Iron Man, the movie, the first movie, and there is a scene where Tony Stark is using a type of advanced CAD where he has a 3D rendering of a gauntlet and he actually sticks his hand inside that 3D image. And that really bothered me because I couldn't think of a way you could get a hologram to do that. One of the limitations with holography is that you have to always be gazing into a modulation surface. You have to be looking into some screen of some sort. And then the light emanates from that screen and comes to your eye. Now, it can be as deep as you want it to be. It can extend to the horizon, or it can come out and tickle your nose. All the objects, the imagery itself can be very deep. But to see that imagery, you have to be gazing at a screen. And once you stick your hand in there, now you have something occluding those rays. And so that really broke the potential for holography. And so I was thinking as I came out of the theater about how you might actually do that. And the best I could come up with at the time was floating nanobots that could shoot, little laser beams in all directions in order to form that image. And so when I saw the particle levitation, it evoked this same idea, these small intelligent scatterers that could create imagery that could wrap around a human arm, for example, or do some of the things that a more traditional display that uses photons alone couldn't do. Whereas this display, which uses a combination of photons and atoms, could do new and exciting things.
Sure. So my understanding here is weak, so bear with me, but my understanding of the display tech we're talking about is you are using one light beam to actually kind of entrap this particle and another light beam to actually illuminate that particle, and you can then move that particle around to draw an image, and you move it faster than the human eye perceives that, and that creates our hologram, so to speak. Is that an accurate understanding, and can we go a little deeper than that?
Yeah, that's correct. So the basic structure and function of the display that we use now is that we take a nearly invisible laser beam, something sitting at about 405 nanometers wavelength, so that's a violet. And the eye can't see very well at that wavelength, so we take that laser and we use it, we focus it through a lens, and the focus is imperfect, so it has what you might think of as a little hole or a minima of intensity, and you can trap little particles in that hole. Right now we're taking little pieces of cellulose and trapping it in that hole. And when you move the focus, when you move that trap, it has the effect of dragging the particle along with it. So we can now basically use that first nearly invisible laser beam as a tractor beam of sorts to drag a particle around through 3D space. And we can drag it to a bunch of potential image points, and when the particle reaches that point, we can illuminate it with visible laser beams, red, green, and blue, to create a point that glows in space with highly saturated laser colors, and then we can essentially use that glowing 3D point to draw out an image in space. And so long as we draw and redraw that image more than 10 times a second, our eyes, by persistence of vision, will see a 3D image, aerial, floating in space that we can see from every angle.
Okay. And then, so to go back to your Iron Man arm example for a second, to do that, you would need multiple emitters, though, right? To be able to draw points that somebody could actually stick their arm into. Is that correct? Because you would still run into the occlusion problem.
Yeah, that is correct for the most part. Now, we did show a little proof of concept, which was a small 3D printed hand. It was just ultra teeny tiny. So we 3D printed a little arm, and then we had the axis collinear with the axis of the arm. So it's the laser beams coming head on towards the arm, like they're going to give each other a fist bump. And then, sure. It's able then to draw rings around the arm without ever having the arm itself occlude the hand, if that makes sense. I mean, how else could you even say that? Yeah, as long as they share an axis.
Yeah, okay, that makes sense. So like the laser beam is in the same axis as the arm, so it can draw the circle around it like this, because the arm isn't including the... Yeah, okay.
That's a special case. We made things easy for ourselves in that example. Sure. But let's say that in general, you don't know where the arm is, so you can't really place the display at the axis, in which case you probably need maybe two emitters. Yeah,
sure.
Multiple emitters potentially.
Yeah, okay.
And you might want that anyway, because if the system isn't perfect, that is to say, if the laser light that's illuminating the particle doesn't scatter uniformly, if you have some splash, some light it doesn't even hit the particle, for example, then it's going to run in a straight line, and then you could hit somebody's eyeball, and you wouldn't want that. So you probably want to be aware of where eyeballs are located, and switch from one emitter to the other, just to make sure that they're not in the danger zone at any point. If you set up a geometry that allows, people to put their eyeballs anywhere.
Sure. So, okay, that makes me very curious. So when looking at, I haven't been able to find this research, but I know I saw it a couple of years ago, but some holography tech from Japan, maybe not holography technically, but volumetric display tech from Japan from a few years ago, they were using really high-powered lasers to split oxygen atoms, I think, to create a light burst in the air, and then they could do that a bunch of times and do something similar to what you're talking about. But then when the researchers was asked, can you interact with it? Can you touch it? They're like, no, very dangerous. So one of the things I'm curious about is what are the kind of the safety concerns? And so is there a scenario where you could have one of these things where it would be usable? I'm fumbling my question. I apologize. What are the safety concerns for this thing then? How dangerous is it to the eye?
So there are two concerns that we're trying to address right now, and they are just particles. Often when people think about, if you scale this, you need lots of particles. What does it really mean to be modifying the environment by sticking these particles in the air? So there's that concern. I mean, people talk about P2.5, which refers to microns, the diameter of these particles, I believe. And we're talking about 10 micron particles. So we're in the ballpark there. So they're thinking, well, you're modifying the environment. Is this safe? So that's one concern. And then the other concern, of course, is that we have lasers and people don't want to get shot in the eyeballs with lasers. So I'll address that one first because I think it is the primary concern. I will say that lasers, of course, are dangerous. We are using lasers that are much lower power than almost anything else people are using in our particular branch of 3D display. You mentioned the plasma display. Originally demonstrated by Keio University, which was the inspiration for the whole thought process of trying to scatter colored light off plasma. So I was thinking of the Keio display, as in that line of reasoning, which is a wonderful display. But yeah, that's right. Flesh searing plasmas in the air. The power required to make those are heavy duty nanosecond and now femtosecond lasers that create those. So we're many orders of magnitude lower in power. So we're in the tens of milliwatts of laser light. And while that's not particularly safe, there's certainly laser pointers sold these days that are more dangerous than some of the lasers we're using.
Sure.
And we have the potential to move into wavelengths that might not be as dangerous. For example, the trapping laser in particular is perhaps the first concern because it tends to be a little more powerful than the illumination lasers that we can turn up and down, arbitrarily. The trapping laser, if we could get the trapping laser to be infrared instead of violet, the safety thresholds for infrared light are much higher than they are for visible and violet. You can throw out hundreds of milliwatts, maybe even watts of infrared light into a room before you really have to worry about eye safety concerns, depending, of course, on a lot of factors. But that's something we've been looking at. Can we move the trapping laser light into the infrared instead of the violet? And then the other question that we might ask ourselves is that, do we really need to illuminate with visible light? So could we, for example, use fluorescent particles and then illuminate with some gentle UV so that there's no splash per se. The light you see is coming from an active particle, active because it's fluorescing, or maybe we're optically pumping a p-n junction, so it's lasing, or it's like its own little laser diode, and it's just glowing of its own accord. And we just provide optical power, at a frequency that we're either not sensitive to, or that has a really high safety threshold. Something along that line. But my guess is that we'll just get really good. We'll have nice uniform particles, and we'll get really good at making sure that all that light is scattered.
Gotcha.
And I think that for the illumination wavelengths, for these visible wavelengths, at least right now visible, I think a combination of a good tight focus, which is, we have, if the light is focusing and then spreading out quickly, even if it starts out unsafe, it gets safe pretty quickly as a function of spreading. The maximum permissible exposure is diffused pretty quickly. So long as then you only have to worry about people sticking their head inside the volume and having laser beams focus at the eye or at the back of the eye. Now there is one other solution in the near term that would alleviate all of these issues, and that is if we just relayed the image. And so if you've ever been to a science museum and you looked at a big spherical mirror, there'll be a box, with a dollar in it, and then it relays the image, so you see the dollar floating above the box. Given a big enough mirror, you can get a pretty good-looking image. Now, it takes some of the magic away because you have to be gazing into that lens to see it. But if we used a lens or a mirror like that one to relay the image and made it movable, you could still see your scene from every direction you could just kind of move that mirror around with you, or it could track you. So you could still walk around and see the scene from every direction. You could go up, you could go down, and it would just have to move around to make sure that you're always looking in that lens. So some of the magic would be gone, but if it were, relayed, then it had all those rays have a chance to go through filters, so that none of the trap light that you're not supposed to see anyway shoots into your eye. You can put polarizers in there to make sure that none of the illumination beams are making it through unscattered, and then all you'll be able to see is visible light scattered off particles, and that's the only thing that makes it back. So if you're going to do something for a kid's science museum or anything where you don't really have control of where people stick their head, that might not be a bad first instantiation.
Gotcha.
Okay. So we might want to come back to the practical limitations, but before that, I'm not a physicist, right? And so I hear about light trapping particles, and I wanted to check how that works exactly, if you can explain it in a layman's terms, because light is massless as far as I'm aware. So how does that trap a physical particle with mass?
So there are actually a couple of different ways, at least a couple of different ways that light can trap particles. The one that people are most commonly familiar with is optical tweezers, which has to do with the fact that for very small dielectrics, for very small transparent particles of high index, if they're higher in index than the surrounding, whatever is surrounding them, if you have light that's focused nearby, there is a calculation that nature does where it tries to minimize energy. And it just so happens that the minimum energy state is if the highest index stuff is inside the highest intensity light. So it will just kind of suck that high index bead or whatever it is right into that focus. And they use that's optical tweezers. But it tends to be limited to very, very, nanometer scale particles, and they tend to be transparent, to whatever the wavelength is that you're using. And then there's another effect called photophoresis, and that's nice because it works on bigger particles, micron scale, tens of micron scale particles, and it works on opaque particles and this is an oversimplification because there's a lot going on here, but it's actually related to the radiometer effect. If you've seen those veins that run inside evacuated or partially evacuated, it looks like a light bulb with a weather vane inside.
Yep. So
that's an effect that initially stumped Maxwell. He made a guess and then had to correct it later. So the effect there, that the force that's actually working, doesn't work if the glass is evacuated entirely. It doesn't work in a vacuum. It needs gas. And so what's happening is, in our case, you have an opaque particle and it sits inside a trap. That means you have high intensity light on either side of it, and it's dim where it's at. So if it wanders off to the high intensity region, on that part of the particle that's touching the intense light, it will start to heat up, and the gas will expand and will start moving from the hot side to the cold side. And that movement of gas imparts a force. You can think of it like a little jet that shoots it back into the center of that trap. And so it's that action, this is actually this expansion and movement of gas, heated gas, that keeps the particle localized. And that can be 1 to 2 orders of magnitude more robust than other types of optical trapping. So it's that's the reason we can move these particles around in the air as fast as we do, multiple G's, of acceleration, in order to make these images in air.
Okay. That's actually really cool. All right. Learning something new all the time. Continuing that line, so you mentioned you are looking into switching the trapping laser to infrared. So what are the challenges there versus the violet? Why would that not work as well, or are there issues there?
That's a good question. I'm not sure that we can really answer them yet. I know that in the literature they have used ultraviolet. There is a paper where they've used, infrared, but they used infrared to trap nanodiamonds so that they could then look at fluorescence and NV centers for quantum applications and this sort of thing. So, and anyway, I mean, the takeaway is that they have done this with IR. We've certainly done it with lots of wavelengths within the near UV and into the visible. So my impression is that it's just a matter of some trial and error to get IR working. My guess is that the absorption is important, and different types of particles will have better absorption at different wavelengths. We have lots of theories about how aerosols might work and at what wavelengths they'd work best. So right now we're taking an Edisonian approach where we have a bunch of little robots that are just trying a whole bunch of experiments. We're trying, let's try graphite as a particle. Now let's try nanodiamonds or pollen or any carbon or toner, all sorts of things. So we try all sorts of different particles. We try all sorts of different traps, and just to see if we can't stumble upon something exciting. And some of the things we've learned have been surprising. We found that nanodiamonds, incidentally, are one of our best performers, better than the stuff that is more typically used, like the cellulose and carbon. Some of these are carboniferous, non-crystalline carbons. In any case, so yeah, those are the challenges. Just optimization, which can take forever. That's the principal challenge that we face.
So to take a step back for a second, then, we touched a little bit on that area of research and what the next steps are. What are the other larger focus next steps in your research that you see coming down the pipe, so to speak, on building these 3D models in space?
So the thing that the question we want to answer is the scaling question. How big can we make this? Its utility is going to be directly proportional to how big we can make these images. And we're pretty well convinced at this point that the strategy that we need to pursue is parallelization. So right now we have one particle moving through a complicated path. We believe that the future will be many particles trapped moving in a simple path. And so a lot of our effort right now is looking at taking a single trap and then copying it. We do this right now we're doing this with something called a Dammann grating. And so if you're familiar with the function of a grating, you send light through a grating, and if it's a thin grating, then what you'll get is many orders of light. So it'll take that first beam and it will copy it and bend each copy so that it's exiting at a different angle. And if you're really careful with how you make that grating, you can get a whole bunch of copies of that first beam that are pretty close to identical in power. So it splits up the power really nicely. So that's what we're looking at, is if we can find a really good trap and then put this Dammann grating in front of it, then we can split that trap into 10 or 100 or 1,000 traps, each one looking pretty much the same with a little bit of degradation. And then theoretically we could then trap 1,000 particles instead of just one particle. The difference now is that they all move in tandem. So they can't all take independent paths. We have to choose one path for all of them. So what we imagine having is maybe a plane of traps, some 2D surface. It's just a grid of trapping sites that's moving up and down, in concert. And as it's moving up and down, we're imaging DMD or something onto that grid so that we could, each DMD mirror then, each pixel is in charge of what each trapped particle looks like. And so we can independently illuminate each of these particles even as they move together through space.
Gotcha.
And that way we've actually made the scanning part simpler and taken that complication and pushed it back to the illumination. So now the illumination is more complicated because we have to simultaneously illuminate 1 million particles independently. But the motion of the display itself is just moving in one axis. So that part becomes simpler.
So I could see that working really well for a 2D dimensional display in space. But if you have 3 dimensions and you want to move particles along the axis that is away from the display, so to speak, then would you be able to make how would you get to a point where you could have particles being controlled at different points along your other axis, so to speak? Would you just need another display then, or multiple displays stacked basically to have layers?
So the next milestone we're shooting for, what we hope will be the next generation, is a geometry that could create Princess Leia.
Sure.
And Princess Leia kind of sits in a cylinder that's tall. It doesn't have much extent in X or Y, but I guess Y would be the tall direction. It doesn't have much extent in the XZ. I mean, maybe a few inches in cross section, but it's mostly tallness. You want 8 to 10 inches in tallness. And so we imagine having some grid that takes care of that entire XZ cross section. So you've got, a grid of particles that fill that entire space that's 2 inches by 2 inches. So now you've made a complete cross section of Princess Leia. Now you just need to scan up and down through that tallness in order to fill your volume. And so that's the geometry we're looking at now. There are certainly other geometries. If you're looking for a circular or a spherically symmetric system, there's other geometries we could look at that would be more optimized for that. If you just wanted, maybe you wanted to create imagery around a globe or emanating from a wearable, a watch or something, you wanted to have it pop up there. There might be different geometries that would be better for that. But we feel like a good first, most simple next step for a scaled parallel system would be just a plane of particles, maybe tilted just a little bit so that you can see all of them, from the projection system, and then one axis scan, which you could accomplish with just a regular galvanometric scanning mirror.
Okay, sorry, I have to ask. Could you define a galvanometric scan?
Yeah, it's just a mirror that sits on an electromagnet. So you turn the magnet on and off, and or you give it a different voltage, and it rotates a stator. And none of these are probably the correct technical terms for the insides of the galvanometric sender, but that's the basic idea. So galvanometer measures current via the magnetic field that it creates, and so you just stick a mirror on that. And now you've got this galvanometric scanner. It's the standard electromechanical mirror, or at least has been for decades and decades.
Gotcha. Cool.
And
so we talked a little. Okay, go for it, Michael.
I'll go for it. So are there, you mentioned, to make an image that persists with the eye, you need about 10 frames per second. Is that a limit of are you only able to go 10 frames a second, or can you do faster than that? What are your limits on trapping and illuminating those particles?
Yeah, so that's a good question, and we certainly haven't found the limit yet. We have drawn images as fast as 30 frames per second.
Okay.
And the smaller we make them, the faster we can draw them in general. We have a lot of variation from one trapping event to another. So maybe we'll trap a particle and it will stay trapped all day long, and it'll still be there the next morning when we come into the lab. And other times, we'll try several times and won't get anything to trap at all. There's an awful lot we still need to understand and refine and improve about optimizing our traps and optimizing our particles. But on a good day, when particles are trapping well, we can yank those around at about 5 Gs without them falling out. So that translates into, a teeny tiny image drawn very quickly, multiple frames, tens of frames per second, or a really big image drawn very slowly in order to get that. So we anticipate that as we actually figure out how to make a good trap and match it with a really good particle, that we could dramatically improve that. But none of that is necessary when we go to parallelization. So in our parallel schemes, that scheme would never feel particularly high accelerations, as if we were going sinusoidal, for example. and we're yanking it hard at the bottom. And we translated into so that's acceleration. So for velocity, we can move a particle about, we think, 1 to 2 meters per second without any issues. And so you could fold that 10 or 20 times, and that basically gives you what your linear scan would be for X number of frames per second, right? So if you chop up 2 meters, divide that by 30, whatever that length is, that's how far you could go in a second and redraw, a 30 times per second, assuming you use both the up and the down for your drawing, which is pretty standard, kind of a Buster-Photonic scan. And then again, the more particles you have, you kind of divide all of all the work of drawing the scene is divided up amongst all the particles that you have in the system. So all that reduces this necessity. So while we could greatly improve, I think, the robustness and the speed and the acceleration of any individual particle, I'm hoping that in these next systems it won't be necessary, that it will be well within the current acceleration limits.
Sorry, I'm laughing. The dog downstairs is louder than it has been in the past, and there's a siren going by. Sorry. In any case, so can you talk to us a little bit more about when you go parallel? You mentioned there for a second of basically diffracting a bunch of your light beams, and I would assume you'd also want to have multiple emitters as well. Are you currently working on doing multiple emitters as well, or are you currently mostly focused on the diffraction you were talking about earlier? I'm just curious.
Yeah. So in this case, I would imagine having only one light emission illumination setup. I'm thinking of having one DMD that is imaged onto a grid of particles, and it's illuminating a million different particles simultaneously. You could theoretically have other illuminators in there, but I don't know. Again, for the Princess Leia example, what benefit that would be initially. The whole occlusion problem is not really the problem we're trying to solve with this next prototype.
Yeah, for sure.
But yeah, certainly for that, let's look at another potential prototype. Let's say that we wanted to create, let's say Elon Musk is throwing up all these satellites. I mean, if he hasn't already doubled the number of a particular class of satellites, then he will soon.
Yeah.
And I think it's NASA now that's responsible for tracking all of this stuff. And maybe they want some system that can allow them to see those satellites. A volumetric display. They put a globe on the table, and now they want to see little particles representing satellites flying around this globe. Then you've got the problem where the globe itself is occluding the illumination of these particles, and so you might need one projector, a system of projectors that kind of run around the equator, and that way you can always reach any point on the globe from at least one of those emitters. And in the simplest case, you've got two emitters, one responsible, each of them responsible for one satellite, and they kind of just track those particles through the air. And then you could see viscerally, you could just know whether or not they're going to smash together, whether you'd have a conjunction, as they call it, and have space junk scattered into anywhere and everywhere. So that's another geometry that might require a different solution. But for this most simple Princess Leia projector, where you're really going for kind of image sophistication and a nice, simple, straightforward scan, I think that a single emitter system would probably be just fine.
Cool. I was just curious. I get excited. I like to imagine the thing 40 years down the line.
So I think 40 years down the line, maybe what we'll be looking at is, so I think the issue is still scaling. What's the next step in scaling? The next step in scaling is to have human scale images. All right, you want to share the room with somebody who's remote. you yourself want to be physically present, and in this case, literally physically present in two places at once or more, then what you could do is, instead of using a trap that's like a bottle that confines in all dimensions, you could use a series of optical straws or filaments where a particle is free to move up and down inside of these. And so if you can then control, you just have a whole bunch of straws that move up and down, with particles inside that can move up and down, then you can create this raster that could be much larger than the ones we create with these bottle beams, with these 3D traps. In fact, there's work done by Shvedov, one of our favorite authors, where he has, in a partially evacuated system, he's got this big long tube that runs the length of his laboratory, and he's moved these trapped particles, a couple of meters in these systems. And so meter scale displays, I believe, could be possible using that filament, a group of filaments, as opposed to a group of bottle beams.
Interesting.
Yeah, you actually preempted my next question about the time frame we're looking for.
Oh, well, 40, I don't think it has to be 4 years. That's code for maybe never, I think, among most scientists.
That's how research goes.
Yeah, I think that I think we have some back of the envelope stuff that suggests that sort of thing might not be that far away. I mean, I can't think of anything magical that we need to do at least a proof of concept for that sort of display. Like I say, already there was a lab demonstration, partial vacuum. I don't think we're decades away from that kind of display. Who knows? It might even be easier than what we're trying to do now. It's often difficult to know on the outset before you actually have a lot of hours in the lab trying it.
For sure. So then, could I ask, is there anything that the people like to get really excited about holograms, so to speak, and making these 3D volumetric displays? I'd be kind of curious, is there any, well, we want to make sure we combat the hype, and we get excited, but we don't get too excited, so to speak. So I'd be curious, is there anything that the media, et cetera, when they're looking at some of the really exciting stuff that you're working on, that they have a tendency to get wrong, that you could set the record straight on, so to speak?
Well, we usually set the record straight when they're talking about holography. That's the one they always get wrong. For the reasons we've already mentioned, the fact that you have to look at a hologram like you look at a television set. You have to be gazing into a screen. But this optical trap display technology is screenless. There is no screen. It really does work just like we imagine the displays of the future will work. So there's very little that we need to do in disabusing people of their expectations besides practical expectations. So we believe that we're 12,000 hours away from that next prototype, which is a significant chunk. And when we talk about that, we're talking about 12,000 professional engineer hours away, not just undergraduate hours away. So we are very early stage research still, and while we're all super excited to make this a reality, it will take a significant amount of research to get from where we are to where we'd like to be, where everybody would like us to be.
12,000 hours is a lot of hours. Do you have a big team working under you, or is it just you slaving away for 12,000 hours?
We've got some excellent students working on this, but it is certainly our hope to bring on some partners, or to have an effort that's more robust. I think we've done enough of the proof of concept work to move into a more aggressive development. And we're actively looking for other teams to help us out with this. It may not be that where this idea was conceived is definitely necessarily going to be the best place for it to grow. You'll have to repot it so that it can grow better somewhere else.
Right.
I certainly have, a short list of people I wish we could get to come work on this. There are some definite luminaries that I think could help push this along much quicker than we could do it by ourselves.
Can I ask who those people are?
Oh, well, I mean, let's see. Well, I don't want to.
You don't have to. You don't have to
I'll
name
keep it.
drop anybody.
I'll keep it on the down low for right now. Who knows?
Okay, all right.
Get headhunted by somebody, but the they don't make it. I don't want to weaken my bargaining here, but yeah, there's a handful of people I think would be really excellent. But then again, it might not be so complicated that a good team of engineers, there aren't a number of good engineers that could make this happen. But there was another point I wanted to make on that. Oh, it was this, that, more than anything else I've done in my career, this or that we've done as a group, this is something that really seems to have captured the imagination of individuals of all ages in all places. We've received, emails from people all over the place, working professionals and people in middle school who say that they just want to be part of the magic, and give me an assignment, tell me what to do that I can help make this real. And so we're trying to figure out ways that other people can help with this. And I think there are some really good ways that others can help us, push this forward quicker. We've created a test rig. I mentioned that we've got a bunch of these little robots running experiments. We've tried to create a cheap version of this robot that you can make with regular fab tools, so with a laser cutter and a 3D printer. In 2 hours or less, you can print out your own little optical trap test rig, and you could collaborate with us to test different particles to see how well they trap, and then that information can be sent, onto a shared database where we could all learn together, which particles work the best, and hopefully soon similar things can be done with different trap types, and then we can take that raw data, that rough data, and then put it on our more expensive machines and get more refined publishable data that will really inform our next generation of displays.
That's really cool. If I wanted to go find the CAD files for that 3D printed model, et cetera, where could I go find that?
So we have a paper. I don't know. I don't remember if it's in review or in press right now, but what we think we'll have is a Jove paper. We chose Jove because it's the Journal of Visualized Experiments. Everything's videotaped, and there's a really strong method section, and it should be a pretty robust how-to for anybody wanting to reproduce this on their own.
Cool.
We do need to think carefully about, there's still a laser involved, and so we'll probably need to add some safety measures.
Legal disclaimers.
Yeah, legal disclaimers. We'll check on liability. My guess is what we'll do is we'll have interested persons who are minors affiliate themselves with their science teacher, at their high school or whatever, and then they can be the responsible adult in the room while they go ahead and try to do their own experiments. I think it's workable. It's none of it is that worrisome that I don't think a little creativity could overcome those challenges.
Sure. You stole the next question out of my mouth. You're pretty good at doing that. I was going to ask how people can get involved, or if they're really excited about your research or want to start working on through these not holography, I suppose, but these volumetric displays. Could we? How do they do that other than going and building that model?
Yeah, so there's so many different ways that people can help. So we already mentioned the one. They can help us directly with our research by building, using, and donating the data they gather from these test rigs. They can also help with, if they have skills. We have people who have animation skills. We're often trying to explain these ideas to people, and often the best way to do that is through nice 3D animations, which can be expensive for us just to buy ourselves, but for those individuals who are willing to donate time to create art and artifacts for us, that's really helpful. In addition to that, we're always looking for the killer app for this technology. We're in a space where we can make images, in about a centimeter cubed reliably, hoping to make him in maybe 100 centimeters cubed soon, fingers crossed. Now, it would be nice. We know that there's plenty of applications for that larger display. But the question in my mind is there an intermediate application, something closer to where we are now in the lab, that would allow us to, draw on the kind of industry interest that might help us really leapfrog and, pull in more funding and bootstrap our way to a bigger display. And it's possible. So, we've been approached by a few dozen commercial venture and other industries, and 80% of the applications they have in mind require a much bigger display than we have in the lab now. But there's maybe 10 to 20% that are probably within striking distance of the kind of technology we have running now. And so we'd love to hear more about that type of intermediate bridging, those bridging applications that might help pull in the resources we need to get from small to big. So yeah, whatever people think might be a good first or second application for this technology, we'd love to hear about that as well. That's another great way that people could help.
We'll let you know if we think of anything.
Maybe I can just throw out a couple. So I mentioned one. That was the idea of tracking and visualizing, aerospace and space surveillance. I think it's good because it's a sparse set of information. It's a complicated 3D path, and there's a lot of value in being able to visualize it spatially. Another example would be maybe visualization for catheterization. So when you have cardiac surgery, they'll put a catheter that'll run through the vasculature of your body, as it approaches the heart, it gets really circuitous. It becomes a very complicated 3D path. And you don't want that catheter to brush up against the artery because that could cause abrasion and that could lead to blood clots and that sort of thing. So it would be cool if you could somehow, maybe if you could you get a high-res MRI beforehand, and you could see, the head of the catheter and the wall of the artery in real time as you're pushing through. Maybe you could prevent those abrasions without having to constantly take x-rays, which is what happens now. You can be under continuous x-radiation for 16 full minutes, continuous, during some of these procedures. So, if they could just, take a quick flash to update the position, then you could have these two circles. That's all it would have to be. One circle that represents, the wall of the artery, and one circle that represents the diameter of the catheter, and you just keep updating that as they push the catheter through. That could be something that could be, very, it's something you could do with two particles or even one particle, but they could have value because of the visualization aspect of it, because of the sparse nature of it. It could be valuable and something within striking distance of what we're already doing.
For sure. So we have gone most of the episode here without explicitly talking about ideas in science fiction other than Iron Man here. And I'd be curious to know if there's anything in particular that has, from science fiction other than Iron Man there, that has inspired you in your life and or your work, etc.
So the geometries that we were initially most excited about recreating were the Princess Leia projection, what we would call a long throw projection, where you have a little orifice on R2-D2 that gives rise to a larger image. That's something that you can't do with a hologram, at least not for a real image. Virtual images are something different. Hologram can make a window into an infinitely large world, but it can't push something out this side of the screen that's larger than the screen itself. And I think that's exciting. I think that the Princess Leia projection, that long throw projection geometry, is exciting because it points to a future where we can have imagery, 3D imagery that is larger than the display that's making that imagery. And I can't think of another example where that exists. Even with a regular projector, you have to project that light onto a screen that's bigger than the projection. But here we could create, you can imagine creating a wearable like a watch that could then, project out a much larger image of a terrain or a disembodied head, at scale. And that's just not possible now, but could be with this technology. And it breaks the tension that we feel between wanting to have small gadgets with big screens or big displays. And I think that could make a lot of things possible that aren't possible now. Then, of course, the other scene from science fiction that we think about a lot is the sand table from Avatar, where they're all sitting around this table, and you have the big tree and different things coming up. The idea of a 3D table is a popular one, and there's been many people who've created instantiations of the 3D sand table, but everyone that doesn't have headgear associated with it requires that still you always be looking down into the table. And if you do the ray tracing, you find that there's really only a very small volume that everybody can see at once while still looking into the table. So it really squashes the height of things that you can show, and it's just not nearly as impressive as that scene in the movie. But if you could create, an optical trap display that could address that entire volume, there's no reason you couldn't make it just as tall as what you see in the movie and have everybody see it at once. And then maybe one more scene that exists only in our imagination, because I can't think of a place that has appeared in science fiction yet. And that is a scene where you have a family sitting in a living room, and they have their optical trap displayed, in the middle of the room, and they're all experiencing something 3D and immersive simultaneously and independent. For example, like the kid is doing math, and she's tracing her finger along a Mobius strip that's projected out there in front of her. And then her mom sitting next to her is looking at the very same volume, but seeing grandpa. She's talking, to grandpa via telepresence. And then dad, who's standing right next to the two of them, is living his dream of being a World Cup soccer player champion in an immersive, football simulation. Now, this can be done with this technology if the following is true. If you could take a particle that only scatters in one direction and not other directions. That way you could have a volume where there's a set of particles that are responsible for the child, a set of particles that are responsible for the mom, and a set of particles responsible for the dad. And they're all gazing at the very same volume and seeing something entirely different. And that, paired with directional speakers, gives them this immersive 3D experience that they're kind of experiencing together. They're aware of each other, can make eye contact with each other. There's no eye headgear associated with this. They're not gazing into a screen. They're fully present with each other, but also at the same time fully immersed in these entirely independent 3D experiences. And that's a scene that I think would be well worth trying to explore and create a proof of concept of.
Yeah, I would love to see something like that. That sounds really awesome. I think we've talked a lot about the holograms at this point. Going with that idea of sci-fi, or just research in general, is there any research or science fiction idea that you'd be interested in finding out more about or seeing built and that you haven't seen before? Beyond the holograms, obviously. So
this is anything, not even related to displays.
Yeah, this is the part of the show where we fish for ideas for future.
Oh yeah, absolutely. So yeah, obviously I'm a big fan of science fiction, in particular Star Trek, and I feel I would just love. We're coming up on First Contact. I think First Contact's year was like 2050s or something like that. We have a short fuse for when we need to have developed warp drive technology, so that we can be contacted by the Federation and inducted into Starfleet. So, that's what I'm really hoping for, is that all these physicists can reduce the energy requirements to something that less than the mass of the universe. So that we can achieve warp drive and make Starfleet happen. I have been very heartened by these solid state propulsion technologies coming out of MIT. That is very exciting to me because it feels so Star Trek-y, right? You have impulse engines well on their way to being a thing, and so I'd love to see warp happen, something that can take us to the stars. Or alternative to that would be optogenetics, making it possible for us to upload our consciousness into computers and then take away the urgency we all feel, we can take our time then, or maybe even just beam our consciousness back and forth without having to worry about all the mass requirements of getting people to and from places in space. Those would all be. I would welcome all those technologies becoming more, robust and available to me.
All right, we haven't touched on any of those quite yet, other than we talked a little tiny bit with Cynthia Chestic on an episode that hasn't quite aired yet, about signal processing for prosthetics, and we did delve into a little bit into brain computer interfaces there, and so it's coming, just slowly. Someday we'll be able to dump your whole consciousness, hopefully.
Yeah, that sounds great. I can't wait to hear it.
Yeah. But in any case, is there anything else you'd like to chat about or promote? Be it an idea, something that you care about or want more people to find out about?
Well, I certainly had the opportunity to make several plugs. I appreciate that. And beyond that, I don't know. I mean, there was just this last idea that I want to make sure is clear, and that is that for so long I was a broken-hearted Star Trek enthusiast in the sense, or Star Wars enthusiast in the sense that in my feed I would constantly get new article pings about, with headlines like Princess Leia is just around the corner or something like this, and you'd click through and you'd discover that it was an article about the Pepper's Ghost or some other Victorian age 3D technology just kind of repackaged, and that can be really difficult for someone who truly wants to see these 3Ds of science fiction come to pass. And so my message to the world is that your faith has finally been validated. That there is a technology that exists that once fully realized will behave exactly the way you imagine. It will be just as magical and aerial and immersive. It'll function exactly the way you expect it to, exactly the way you'd hoped it would. And I think for a lot of us that will mark our entry into the future.
For sure.
I think the movies had made it very clear that the future is not the future without these displays. And so I think that the future is possible, and I think it's well on its way. I think it's going to happen, and we're all going to see it.
Love to hear it. There's a lot of these technologies that we can't say the same about. So it's good to hear about something that will live up to the hype.
Well, I think that's about it, unless there's anything else you want to chat about. So thanks a ton for chatting. We really appreciate it.
Yeah, my pleasure. Favorite thing to talk about.
For sure.
You've got the right job for that.
And that's a wrap. So thank you so much for listening to this episode of Sci-Fi to Reality. We hope you enjoyed it. We also hope that you go check out our website, www.sci-fi-to-reality.com. That's www.sci-fi-to-reality.com. You can also go check out our Facebook page, Twitter, Instagram, the whole gambit. And you can also find this podcast wherever you personally get your podcasts, along with our YouTube page. I hope that you guys enjoyed it. Give it a share, comment, like, subscribe, all that good stuff for the various recommendation algorithms. We really appreciate it. Thank you so much for listening, and we'll see you in the next one.